Right, so welcome to the bonus video. So this is another example of using Newton's third law of motion, as well as some changing coordinate systems. So this is number 40 from the back of the chapter. So the image, the reason the angle is like that is it's the same image for 2, and the image says 20 degrees, which I accidentally used. So theta here is 35 degrees. So we have a 4-kilogram box and so forth. Here we actually have a pulley instead of a random rope. So that makes it a little easier to understand. So I want you to go through. So for part A, this is going to be, we are holding this mass on the incline in place. In part B, we're going to let it go and see which direction stuff moves. So go ahead and draw, in general, the free body diagram for both of the blocks, but don't go through and solve for A or B yet. All right, so let's go ahead and draw our free body diagrams. I don't like using the numbers inside of it, and I kind of want this to match the previous example a little, so I'm going to have B and A. So B here is on a incline, and it's going to have a normal force that is perpendicular to the surface. I'm going to have the force due to gravity for block B, and I'm going to have some tension. I have a frictionless surface, so I don't need to worry about friction in any way, shape, or form. And we'll come back to the coordinate system in a second. So for block A, I'll just have tension. It's going to point upwards, and I'm going to have the force due to gravity for block A. So for drawing my personal coordinate systems, again, I like to think about it in the direction that the object is going to move. Block B is 4 kilograms, and block A is 2 kilograms. So block B is twice as heavy as block A. So I have to guess, does block A pull it down, or does block B pull A up? It's a 50-50 guess. If I guess wrong, all it tells me is that I am going in the other direction. So there's nothing wrong with picking the wrong direction. I'm going to say that I'm going to move up the incline. So I was going to put X up the incline and Y up the incline. Sorry, this is 35 degrees. So because I think that the 4-kilogram block is going to move up the incline, that would mean that A moves downwards. So these are going to be the free body diagrams I use in order to go through and solve this question. So again, I have chosen block B such that I am only moving in one direction, in this case X. I am choosing my coordinate system for A such that the direction I'm moving matches the direction I am moving for block B. Because that way, in part B I'm accelerating, I don't need to go through and worry about that particular direction change. So let's go ahead and let's do part A. So in part A, we're going to hold block B and then calculate the tension for block A. I think this part's very weird to include, but sure, we'll do it. So we have tension, we have the force due to gravity. In A, we have our coordinate system that we introduced in the last one. So if we look at the X direction, because that's the direction tension is in, I'm going to have negative tension plus force due to gravity A, and stuff is being held so that it's in place, so I have an acceleration of 0. I can just replace my force due to gravity variable with its equation, and I can just rearrange this to solve for the tension. Mass A is 2.0 kilograms. The acceleration due to gravity is 9.8 meters per second squared. Taking that and plugging it in, you're going to get 19.6 newtons, or the tension is about 20 newtons. This question, or this part of the question, we've done before, right? We've said, hey, this is stationary. What's the unknown force? This part here is nothing new, other than we've changed the coordinate system and now gravity is an x. It's part B where we need to start utilizing Newton's third law of motion. So let's go ahead and do that. So let's think about our two blocks and writing out Newton's first and second laws for these blocks. Because in part B, we've let go of block B, and we want to figure out which direction it moves and the tension. So direction is equal to something and tension. We want that new tension value. So we are accelerating in this case. We're starting from rest because we were being held in place. We're letting it go and we're seeing which way we're going to move. We're going from rest to motion, which means we must have an acceleration. So if I look at let's start with block A. The sum of forces in X, I'm going to have force due to gravity minus tension is equal to mass A times the acceleration, times the acceleration. Or again, I can rewrite this as mass A g minus t is equal to mass A unknown acceleration. The y direction is going to be really easy. I don't have any forces there. I don't need to worry about it. So I've written out the first law, and in the case of my x direction, the second law of motion for block A. If I look at what I currently don't know, I don't know the tension, and I don't know my acceleration. However, I am connected to block B, which also has a tension and also has an acceleration. So I'm going to be able to go through and use block B and block A together to solve. So let's go ahead and look at the free body diagrams for block B. So I'm going to write out my Newton's first and second law for block B. So let's start with X. So my normal force, because I've tilted my coordinate system, is only in X. Tension is in my positive X direction, and then I'm going to have negative force due to gravity for block B, but not all of it. Again, I can do my triangle. X is going to be opposite, so it's going to be sine theta, and this is going to be equal to mBg. So this is Newton's second law of motion for block B in the X direction. And again, I can simplify this. I don't know if it's simplifying, but I can write it out in a way that's a little bit more visual. So again, I don't know my, oops, these aren't G's, these are A's. Keep getting ahead of myself here. I don't know my tension and I don't know my acceleration. So I have two equations, two unknowns. Even though we're in this question, we're not going to need the y direction. Let's go ahead and practice writing it out. I'm going to have normal force I'm going to have some force due to gravity in the y direction. If I look at my triangle, it's going to be adjacent, so it's cosine theta, and it's going to be equal to 0. So this would be Newton's first law of motion for the y direction for block B. So if I had friction, I would need to use this y direction to solve for friction, or to solve for the normal force, plug that into friction. I don't in this case, so I don't need to worry about it. So let's figure out how are we going to go through and solve this. And so for that, we need to just focus on the direction we have of motion, which is going to be x for both of my shapes, or for both of my blocks. Before I do that, I want to recap what we've been doing. So we drew free body diagrams for block A and B. We chose a coordinate system, and by we chose, I chose. I don't know what you've chosen. I have chosen a coordinate system such that all of my motion for block B and block A is in positive x. Or, if I guessed the direction wrong, it'll be a negative x. But they are moving some way in the x direction. I have written out the first law for the y direction for both blocks, and the second law for the x direction for both blocks. So I have gone through and written this out. I now have two equations with two unknowns. So let's look at them again. All right, so from block A, I have the equation negative tension minus MAG is equal, it should be plus MAG equals MA times the acceleration. From block B, what I have is positive tension minus MBG sine theta is equal to MBA. So I have two equations with two unknowns. I have tension and I have acceleration. So how I'm going to go through and solve this is I have to choose. Do I want to solve for direction first or tension first? I'm going to solve for direction first. So solving for direction. And what I'm going to do is I'm going to call these equations 1 and 2. Because that way I don't have to write out as much as to explain what I'm doing. I'm going to solve 1 for tension. Because what this is going to do is once I solve 1 for tension, I can take that and I'm going to be able to plug it into equation 2, and I'm only going to have one unknown, acceleration. And once I have one unknown, everything else I actually have values for, I can solve and I can be done. So I'm going to solve 1 for tension. So I'm going to have tension is equal to mass A times the acceleration due to gravity minus mass A times the acceleration. I'm going to call this 3. I'm going to plug 3 into 2. So that means I'm just going to replace, I'm going to replace tension with mass A times G minus mass A times A minus mass BG sine theta equals MBA. So the only unknown I have now is my acceleration A. So I can rearrange my equation, solve for A, and what's going to happen is I can either have a positive or a negative number. If I have a positive number, that means that block A is going to move down and B moves up the incline. If A ends up being negative, I guessed my direction wrong. A is going to move up and B is going to move down the incline. So even though I've guessed some stuff, once I solve for the acceleration, I'm going to have an answer on if I guessed right or not. So skipping to having the acceleration isolated, I'm going to have mass A minus mass B sine theta multiplied by g divided by mass A plus mass B. So I've just isolated my acceleration value. I have all of these numbers. Mass A is 2 kilograms minus 4 kilograms times sine 35 multiplied by 9.8 meters per second squared divided by my 2 kilograms plus 4 kilograms. Taking this and plugging it into a calculator, I got negative 0.4807 meters per second squared. So I have a negative sign associated with my acceleration. So this tells me that for the direction, A moves up and B moves down the incline. I now have the direction for my boxes. Because of the coordinate system I've chosen, I could simply just say they both move in the negative x direction. And this is why I personally really like putting my coordinate system such that both blocks move in the same direction. I didn't need to think about setting x equal to y or anything like that. It was just, hey, they're moving in the same direction. I can just use the x direction in all of my calculations. This personally is why I like to do this. If you don't want to and you want stuff to move in only y, or maybe you're okay mixing up your two directions together, that's fine. It's just you need to be very careful that you mix them correctly. So the safest way to do this is to just use motion in one direction for both blocks. So now that we have our value for acceleration, all we need to do is plug it into one of our equations that has tension in it. So I'm going to use that tension is equal to mass A, G minus A. Mass A is 2 kilograms. G is 9.8 meters per second squared. Minus negative 0.4807 meters per second squared. Taking this and plugging it in, I got 20.5613 newtons. We're being picky with sig figs, 21 newtons. You could also use the equation for block B. It's just I don't want to have to deal with using sine. I don't want to do it, so I would rather use block A's equation. But if you use block B, you get the same value as well. So in this example, we've dealt with an accelerating system that has motion in two directions if we use a standard coordinate system. We still could have solved for it, but it is going to be much more complicated in doing so because we have to now consider the magnitude of block B, so AX and AY, that would need to be used to go through and solve in relationship to block A. So tilting the coordinate system is an extremely powerful tool that we can use that makes it so that we can solve questions much simpler. All right, so that's going to wrap it up for the bonus video. If you have any questions, let me know.